Dear friends, you can't think of high load without using all of your available resources. So our next speaker will tell us how to make all your CPU cores happy. So please welcome Vladislav Shpilevoy.
Hello everyone, 1, 2, 3. So many people today. Exactly as many as usual in my talks. Yeah, anyway, let's start. My name is Vlad. I am a C and C++ developer with roughly 8 years of experience or so, at least of paid work. And currently I work at a game dev company called Ubisoft. Some of you probably heard about it, a few. And here I work mostly with low-level networking, some bits of system programming and likewise. And there, while doing a complete rewrite of our networking stack in one of game engines, I managed to design, I hope, fairly cool algorithm for doing so-called task scheduling, which improved a lot performance of our online backend in this game engine. Yeah, I shouldn't step out of the red lines. And today I share this algorithm in the form of this talk and an open source C++ implementation of those algorithms. It's very hard to do open source in Ubisoft, I can tell you that. Yeah, it also doesn't have to be C++, don't be afraid. You can do it in some other language as well, and today we concentrate just on the algorithms, not on the source code. Point is not in C++ today. It just happened to be the first implementation. My talk will follow the plan. First, I explain what is task scheduling precisely, how it's normally done, what are typical problems, at least known to me. Then how worked an old task scheduler in my game engine, and then how works the new scheduler, and then we briefly talk about formal verification, benchmarks, and future plans. So in task scheduling, at least today in this talk, I mean any kind of execution of callbacks, functions, or some other kind of code, whatever you can imagine, which we will just call tasks. A few examples. Tasks can be callbacks in a thread pool, or tasks can be watchers in an event loop like libef or a libevent, or tasks can be coroutines in any kind of coroutine engine like fibers in Tarantul database. All those are task schedulers, really. So in here I show you a very trivial task scheduler done in C++ like pseudocode, which we will need later, both the code and the scheduler. It has just a single thread. It has a mutex locked queue of callbacks, and what thread does is just executes callbacks one by one. This is basically the simplest trivial scheduler you can do, and let's see if such a basic scheduler can solve a real task, which I had at Ubisoft. There are tasks executing requests coming to a server, and they handle save game blobs. And there might be tens of thousands of them, and they are CPU intensive. Some of them might take milliseconds of pure CPU time. And most importantly, those tasks, those requests, they have multiple steps, each of them. Each request has to log user profile in a database, download save game blob from another database, process the blob somehow, update it or whatever, upload it back, and then log the user profile. As you can see, there are multiple network exchanges. As a result, 99% of time or even more, the task is not doing anything. It just sleeps, it waits for network input. There isn't much work during the task lifetime. So let's see if this basic scheduler can solve this task. Well, it can. Firstly, it will choke on the CPU because there are CPU-intensive tasks, some of them, and you need multiple threads to handle this kind of load. Secondly, what is worse, this scheduler can't postpone blocked tasks and do other tasks while the blocked tasks waiting for events like network input. We don't want to block the entire thread just to wait for network input for a single task. And this scheduler is not able to solve this. So we need for tasks to be able to yield. And that essentially means we need support for coroutines. The game engine I'm working with had good enough scheduler for a while, which could do the job good enough. There was a thread pool. each thread in this thread pool had a list of own tasks pinned to those threads forever. And then each worker thread would, when new tasks appeared, they were distributed across the worker threads pinned to them. And those worker threads were running infinite loops, updating all their tasks with some fixed period, like once per second, once per 100 milliseconds. This stuff is simple and it could scale to a certain extent because it had multiple worker threads and tasks were not blocking each other. Let's call this scheduler updater, because what it does is there isn't much scheduling, really, it's just updating with some fixed period. I wouldn't even call this scheduler. This updater, despite its simplicity, had some typical problems. First of all, it was unfair, meaning that tasks pinned to threads would make their CPU usage unbalanced. It could be that some of your workers will get heavy tasks and some workers will get light tasks. If it will happen even if you use round robin, which is supposed to be even, and even if all your tasks are the same, like in my case, every task executes the same 5 steps. But those steps can take different time. For instance, save game blobs can vary in sizes from kilobytes to megabytes, and their processing obviously will not take the same time. As a result, some of your threads will be in 100% CPU usage, some of your threads will be in 50%, some will be in 10, 0. It is unfair, and tasks in the overloaded threads will have worse latency. They will have to wait longer in those queues inside the threads. Next problem is polling, which in this particular context again means repeatedly calling task callback, updating all those tasks with a fixed period regardless of task state. So we just, regardless of whether task has work to do, we still update it. And if you set this polling interval to a too high value, you will have too high latency. Imagine an example when we have a task with just 3 steps, each step taking 5 milliseconds, and you will update it once per 100 milliseconds. Then your task will take at least 215 milliseconds to execute. But that is not always needed. You don't need so much time most of the cases. It could be that your task has events to process before 100 milliseconds expire, but still you will wait entire 100 milliseconds, and there will be unnecessary waiting, increasing your latency without need. If you try to fight this problem set to low polling interval, you will get other problem that you update your tasks sometimes without need, before they have events to process. How bad is it? Well, imagine like unnecessary update, also known as spurious update, spurious wake up, costs us just 10 microseconds. It's not too much, but if you have 10,000 tasks and you update all of them at once per second, you waste 10% of your single CPU core. 100 milliseconds just wasted on unnecessary work. It's not even work. And this problem was actually real in one of the backend servers when at certain load, the server was spending more CPU time doing those unnecessary wake-ups than doing actual work. To summarize what we need from a really performant scheduler, first of all, it should be fair. There shouldn't be pinning of those tasks. Secondly, it should have coroutines support for tasks to be able to yield. And thirdly, we should make it event-based. There should be zero polling, if possible. And those features are achieved in a new scheduler, which I call the, well, task scheduler, I suppose. Because this is what it is. Imagine like we have a process. Yeah, first is a plan how we will discover it. I will show you the pipeline, the big picture, how it works, and then we will look at individual parts when you will already know what they do. Imagine like we have a process with multiple threads, and somewhere in this process lives task scheduler object. It can be C++, can be C#, can be Java, can be Rust, it doesn't matter. There is an object of type task scheduler, and those threads, all in the process, they post tasks into the scheduler. Those tasks execute requests or some other work. They have just callbacks of some sort. Those tasks gather in a so-called front queue inside the scheduler. Then a scheduler will pick up those tasks out of the front queue, all of them at once, and they will inspect each of them individually. And it will see that some tasks are ready to be executed right now, the red ones. They want to be executed ASAP. And other tasks don't want to be executed now. They have a deadline in the future. they want to wait for some time or for certain events. It means these are yielded tasks. They go into a wait queue to be executed later. And then at the same time from the wait queue, scheduler will pop older tasks which were here already waiting since previous iterations and now their deadline is up or they were woken up explicitly as coroutines. Either way, all those red tasks ready to be executed join in the ready queue, the third one. And from here, they are picked up by individual threads one by one to be, well, executed. And that is the whole pipeline. It's a big picture. I hope it's not too complicated, although some of you already may have a question, who does this part? There are worker threads doing tasks, but who does the scheduling itself? How I see it sometimes done, and it's the most trivial, naive way, although most of the time it's good enough, is that people do special thread doing just the scheduling, and other threads do the tasks. So threads have roles. I don't like this approach because it forces you to have always at least two threads. One for scheduling, one for executing. And I want my task scheduler to be functional with just one thread as well. For example, I just want to use coroutines. I don't need to handle high load. I only want coroutines features. Then one thread should be enough for me. So what I did is that those worker threads, they compete for doing scheduling depending on who of them is idle, sometimes. Imagine like this big rectangle, this one, it's a room with a single key to this room. And the worker threads sometimes try to pick up the key. Whoever does it first opens the room, enters it, does the scheduling, populates the queues, leaves the room, locks it, and gets back to executing tasks, some of which it just scheduled itself. And then later some other thread will pick up the key and so on. This process just constantly repeats depending on which worker is idle right now. Let's inspect a visual example to improve understanding. Imagine like we have 5 tasks. They go into the front queue. And one of the worker threads has the scheduling key. It will take those tasks and see that a couple of tasks have a deadline in the future, so they are placed in the into the wait queue. And 3 tasks ready to be executed, they go to the ready queue. Now all the tasks start doing tasks. All the workers start doing tasks. The scheduling key is not used by anybody. Each thread is not idle, they are doing actual work. And now a couple of tasks are executed. They are finished. And suddenly those waiting tasks expire. Their deadline is up. So one of the worker threads eventually will pick up the scheduling key and will notice this. It will move the tasks into the ready queue. In the meantime, in parallel, some other thread executed the last of those first 3 tasks. Now those 2 tasks are picked up by random threads from the ready queue, they are executed, and some other random thread will pick up the scheduling key and wait for new tasks in the front queue. And then the process will eventually repeat when new tasks appear. This is how the pipeline works. I hope it is understandable. Now what I need to implement this all. The language or standard library which I will use should give me access to coroutines, to mutexes, to condition variables, to containers like arrays and lists, and not critical for algorithm, but critical for performance, I need lock-free atomic operations. What are those lock-free atomic operations? Just in case somebody doesn't know what they are, there is their pseudocode briefly. I will need 3 operations. First is so-called atomic load, which will read value by some given address from some variable with respect to so-called memory models, which we can Google afterwards. They're not important for the talk right now. Anyway, there exists this atomic load thing, which is almost like reading a variable. Then I will also need atomic compare exchange, also known as conditional assignment. And I will need atomic exchange, which sets new value to a given address, sets new value to a given address and returns me the old value. And those atomic operations, these pseudocode pieces, they work like if they would be surrounded by mutexes, by mutex locks, although in fact they don't need any mutexes. Those atomic operations are usually implemented as hardware instructions right on the CPU. Without mutexes, they are nonetheless lock-free and thread-safe. And they are linchpin of a lot of performant lock-free thread-safe algorithms. as we will see some of them today later. So following the pipeline, we will start from the front queue. We know about it that it collects tasks from multiple threads, external threads, and it flushes them into a single thread, the current scheduler worker. So we can tell that this is a multi-producer, single consumer queue. Very helpful information, actually. So this is a common notation for naming queues. We say multi or single producer, multi or single consumer, and all those combinations produce types of queues. This is a multi-producer, single consumer. We also know that it will experience high contention, most likely, because I can have like 10 threads or more producing tasks, millions of tasks per second. I want this case to be functional, so there will be high contention. It means I should avoid mutexes if possible. They will most likely choke on this kind of load. In a normal queue, you would have to remember two positions, head and tail, to be able to push and pop items in order. And updating two variables in a lock-free way using those atomic operations, it's quite an non-trivial task, I can tell you. And I want to avoid this if possible. So the idea here is, let's make this a stack instead of queue. At least store as a stack. Because a stack is just a single variable, it's a top item. It is much simpler to update in a lock-free way. This is almost literally the entire code to make this queue. Pushing works like you would normally expect a stack work. We get old top item, link it with a new item, try to set a new top. Except that we do it using atomic operations. And if some other thread will interfere after load but before exchange, then our compare exchange will fail and pushing is retried. No mutexes, thread safe, lock-free. It is quite fast. And popping works in a bit surprising way, unusual, you can say. And what it does is it replaces top item with null, which effectively results into taking all the items at once, not one by one. In this implementation, popping items one by one out of this queue is not possible, and we don't really need it in the scheduler. And also you have to reverse the result. Because items were pushed as queue, stored as stack, reversed, we have to reverse it back before return to keep the order. These are only two downsides. We can't pop one by one, and we have to reverse the result. But on the other hand, the queue is completely thread safe, lock-free, and most importantly, it's weight-free as well. And about performance, how good it is or bad, we will see in the end in the benchmarks section, where I will show you how all those queues perform. Next part of task journey is the waiting queue, which stores, as we know, yielded tasks, some of them having deadlines in the future. What we know also about it is that we have to be able to quickly pop all expired tasks out of here, which want to be executed. Simply because everything here has to be done quickly, so it has to be done quick. And we also know that this queue is accessed always by one thread at a time. It lives inside the scheduler room, which is always accessed by one worker at a time. There is no concurrency, which gives us quite a lot of freedom what to use, and still we use just binary heap. Because it's simply the best choice here, and you will see now why. So here I sort in these binary heap tasks by deadlines, basically. So task having closest deadline, so minimal timestamp, will be stored on top of the heap. And that means I can instantly, for constant time, tell if any task has expired in my heap, because if it did, it will be on top. And I have logarithmical time for updating the heap for any kind of update. Insertion, removal, doesn't matter. Very cool, very simple data structure, very tasty complexity parameters. And just in case somebody of you don't know what heap is, firstly, you should get to know it. It's really useful and simple thing. And what it is, it's essentially in the simplest implementation, it's a perfectly balanced binary tree, where each node's value is less than values of its child nodes. That's it. That we call minimal binary heap. And if you reverse the orders to greatest item on top, then it's called maximal heap. Implementation is it's really trivial, and it works very well here. About benchmarks in the end, and next stop of the tasks is ready queue. It stores tasks which can be executed right now. We know that it is populated by one thread and consume the current scheduler worker and consumed by multiple threads, all the workers, which means it is a multi-consumer single producer queue. Very helpful. We also know that this queue it will experience high contention because I want to have sometimes 10 worker threads executing millions of tasks per second, then there will be high contention. And I want this case to be functional again. However, sadly, I don't know a nice algorithm for unbounded and log-free version of such, of any multi-consumer queue really. And I need precisely unbounded, so not limited in size. That means unbounded. I don't want any limits inside my scheduler. You can add them on top, like limit total number of tasks you have, but I don't want the scheduler limit what you can do with it. You can add limits on top if you want. I don't want the limits inside. However, I know very simple implementations of log-free bounded queue and log-based unbounded queue. Let's briefly take a look at them, we will need it. The bounded log-free is really simple, it's just a cyclic array where indexes are atomic variables, basically. So pushing is trivial with a normal non-thread safe cyclic array. The only difference is that the right index is incremented atomically. That's it. And popping items is a little bit more complicated, so we have to take what is the current read index, take the item, try to increment read index. If atomic compare exchange fails, we retry. It's very similar to how push works in the front queue. It's almost complete source code, which you can fix just a little and compile and it will work. And the unbounded log-based queue is just, I hope I don't need to explain this. So it's just a mutex and the list, we lock mutex on every operation. It will be unbounded and unfortunately log-based. So what I had was the craziest idea. Let's combine those approaches. The enemy is not the mutex. We should rethink our priorities. We have to get rid of the contention, which doesn't mean we have to get rid of the mutex. Mutex can be good if you don't contend on it too much. Let's target the contention. So let's take the targeting contention means we should log the mutex less frequent at least. So what we should do is let's take the bounded log-free queue and make an unbounded locked queue of log-free subqueues. Let that sink in. What happens is that the single producer will push new items to the last block in this queue in a log-free way. When the block becomes full, it takes mutex, appends new block, switches to it, and will fill this block in a log-free way, and so on. Consumers work similarly. They will attach to the first non-empty block, consume it in a log-free way. When the block becomes empty, they switch under a mutex lock to next subqueue, consume it, and so on. So as a result, to see the benefit, imagine like subqueue size is 10,000 instead of 4, like here. Then what happens is you take mutex lock once per 10,000 operations. The mutex is here, but contention of the mutex is 10,000 times reduced. It allows you to keep the code relatively simple, and you almost have zero contention on the mutex. You will not see it in any flame graphs. It will never be a bottleneck neither of this queue nor of the scheduler itself. But still mutex is here, and it helps us to keep the code simple, basically, and contention is reduced like we wanted. The only problem here is that consumers will need explicit state. This queue has no just two methods, push and pop. There is method push, and consumers is a separate, they should be separate objects registered explicitly here. Why? Because if consumers are not registered, then it means on every pop they would have to locate first non-empty block. Locating it means they have to access the list of blocks, which is protected with a mutex, which would result in locking the mutex on every pop, which we exactly wanted to avoid. So consumers have to register themselves as consumers, as special objects. They have to keep a reference at the last used block to continue from it on next pop, which is fine for scheduler because scheduler has fixed set of threads. which simply register themselves as consumers when they start, and then they live just fine. For scheduler, this is not really a problem. And let's inspect a visual example again to improve understanding. So imagine there is queue, single block, it's empty, 2 consumers, 1 producer. Producer pushes 3 items in a lock-free way. One of the consumers consumes 1 item lock-free. Now producer pushes another item lock-free. It will see that the block became full. So it acquires mutex. It appends a new block, switches to the new block, releases the mutex. Pushes another 3 items lock-free. And now one of the consumers consumes 3 items in the first block lock-free. It sees that the block is empty, so it acquires mutex, switches to next block, releases the mutex, consumes another item lock-free. Now another consumer wants to pop something. It will see immediately that its current block, last referenced one, is empty, so it also takes mutex lock, switches to next sub-queue, releases the mutex, consumes 1 item lock-free. We pushed we made well, many operations and locked mutex just a few times, and this is just 4 size sub-queue. And imagine like when it's 10,000, there wouldn't be a single mutex lock. And the old, the first sub-queue which became empty, it's no use for us anymore, so we can discard it. It can be freed or reused if you want. If it's 10,000 block, then we don't want to allocate it every time when producer pushes a new block, so we can reuse it. We can append it to the beginning again. Or you can free it. For the algorithm, it doesn't matter really. Although in TaskScheduler and C++, it is reused. So our path so far is that we saw the big picture, the pipeline. We saw individual parts, these 3 queues. Now we shall take a look at the coroutines. Sadly, we don't have much time to take a look at their implementation, and we already saw the main part anyway. The wait queue is core of the coroutines. That's how yields work. The yielded tasks are stored in the wait queue, so that's their main part, and we already saw it. For the details of the implementation, I count on your questions after the talk, and it's also open source, so you can see it in the source code, where I left plenty of comments explaining what works and most importantly why. And it's not too much complicated, just a lot of corner cases. Here I will show you just the usage patterns. What features in those coroutines are needed and why, with examples. Let's inspect a bit simplified version of my original example about save game blobs. Here, instead of 5 steps, we have just to start download of a save game blob and handle the result. Just 2 steps. We know that while the task is waiting for a response, it has nothing to do. It needs to go to sleep and let this worker thread handle other tasks while we wait for a response. We also know that we can't wait infinitely. We can't wait for our save game for hours. It should be like, there should be some sort of deadline in a few seconds, after which we should abort the request. There should be some deadline. And also, if response finally arrives, how will my task know it? It's sleeping in the wait queue. It's not polled anyhow like an updater scheduler. It's not waking up, but still I have to deliver somehow an event into the task. So it would wake up before the deadline. So that's when I will need task yield, task deadline, and task explicit wake up. And now we will see a short example, which again looks almost exactly like real code in production, just a little bit simplified to fit onto the slide. Imagine like we have again a global task scheduler and a global HTTP client of some sort, and a request arrives to my server. I create a task for this request. My task will have a callback download, just a plain C function or something, whatever you want, and I post this task into the scheduler. Then eventually SAP, it will be executed, my callback download. Here what I do first is I set what will be my next step. Next step will be handling the result when it arrives. Then I start the actual HTTP request, asynchronous one. I assume my HTTP client is asynchronous. And I give it a future callback, lambda function, or again, whatever your language has, which will call wake up method on my task when the request is ready. So that's how I will deliver an event into my task. I will call wake up on it when the request is done. Then I start waiting. I post myself into the scheduler with 5 seconds deadline. My task goes into the wait queue, which we saw. It sleeps here, waits for network input. Eventually, something happens. Handle result is invoked in some worker thread. I have to see why is it invoked. It could be that my task has expired. So I literally call is expired on my task. If it's true, then probably response hasn't arrived, 5 seconds passed. So I cancel the request and I continue waiting for the cancellation to be complete, to properly free resources and all. So I cancel the request. Otherwise, if it's not expired, it means request has completed. So this wake up future callback was finally called. It could be a success, response arrived, or it could be an error, or it could be my own cancellation on a previous wake up a few lines above. So handle result might be called second time already. Either way, I just handle the result, whatever that is, and delete the task. Basically, that's it. I hope you can see that this is quite a nice approach, at least in my opinion, when you don't have a single sleep. You don't have, like this polling is usually done, update sleep 1, update sleep 1. Very nice, and no. And there is no single sleep, not any single spurious wake up of this task. And this looks like clear state machine with states expressed as callbacks, download and handle result, clear states. And also the cool part is that this is all completely log-free. These coroutine features, wake ups, deadlines, they're all log-free. There is no mutex per task which we have to log on every operation. There is no mutexes except which we saw in the radio queue and a couple of others in other place. So this thing has very low overhead, as we will see in the benchmarks later. And how can I, if not guarantee, then at least improve chances that all this cool stuff it works at all? Maybe I have unit tests, quite a lot of them actually, but with multi-threaded algorithms, the thing is that you can't be sure that you tested everything, even if you have 100% code coverage. Doesn't mean much. However, bugs can literally stay hidden for years, and you will find them in the most inappropriate moment. Good for us, there is a way to improve chances that the algorithm itself is correct. We can't validate implementation to be absolutely correct, but it can be done for the algorithm, for the idea behind the implementation, which at least will improve our sleep at night. If we can't guarantee anything, but we can improve chances quite a lot. The solution is TLA+, which stands for temporal logic of actions. It's a combination of mathematics and temporal logic. And TLA+ has a language and runtime. In this language, you can describe any imaginable algorithm, like literally, I implemented a queue in C++, I can validate it here. I have a cluster of microservices, I can validate it in TLA+ as well. I am going to a shop for groceries, and I also can validate, I can algorithmize it and validate that I didn't forget to buy anything. I mean, when you study TLA+, there are literally examples like validating a game from Die Hard movie, validating car racing, these are simple examples from which you start studying. Anyway, based on your TLA+ specification, the language runtime will break down your algorithm, your system into a graph of all reachable possible states of your algorithm. It will make a full scan of your system for the algorithm and validate every reachable state. And what is valid, what means validness in your case, you define yourself using this language in some set of invariance assertions. Let's inspect a short example again. Assume that I have implemented a queue in any language. Here I verify the algorithm, not the source code. First, I have to define system granularity, what objects I have in my system, what agents which will interact. And here I define storage called pipe for the items of my queue and some counters and limits. Also, then you have to define actions in your system. First action is always init, initialization. It is executed one time when your validation starts. And in TLA+, each action, including init, is a set of mathematical formula, basically. With formulas expressed as ASCII graphics, as you might notice, with operators like list of items in math, or and operator, or operator, or all items in the set comply with the condition operator and other mathematical operators. And here what I do is I say that my pipe should be an empty set, empty list, and my counters of received and sent items are 0. That's it, very simple. Then I have to define my first useful action, which will do something. We will call it send or push, whatever. My way, there are multiple ways how to define actions. My way is that I split each action into two parts. Firstly, I say when the action is possible. So here I say sending is possible when? Well, it's quite clear, right? Just when length of my queue is less than limit, so as it wouldn't overflow, and when I haven't sent all items yet. Then in the second group, I say what changes will be done when the first group is true. So here I say add a new item to storage pipe and increment counter of sent items. As items, I just use numbers. However, how to distinguish those two groups? I mean, if I remove this highlighting, you can't tell there are two groups. The distinguishment is done with a single quote sign. To distinguish conditions from changes, you use this quote sign to say that this is not a variable, this is a next value of your variable. The problem is that TLA plus has no assignment operator. It's just, there is no assignment in math. There are only conditions. The closest thing we have to assignment in math is a comparison equation. So what I say here is literally new pipe equals old pipe with new item appended, which in normal languages usually results into assignment. But in TLA plus, you have to deduct this yourself with the single quote sign, which you get used to, actually, after some time. So in TLA plus, the entire action is just a set of mathematical conditions. There is no separation like I do. I just find it simpler to understand your own code and to write it if we try to make it similar to normal imperative languages. So I split it into groups. More explicitly even in the full specification than here. Then we also define action receive in a similar manner, and then you have to define what is validness in your system. So you have to define invariance. You can have more than one. Here I just have one. In my invariant will validate that in every reachable state of a full scan of my entire system, the queue is always ordered, queue never overflows, and items are always received in correct order. And then with a few technical steps, even from the command line can be done, you run this validation. And it will give you one of two results. Either n states are found, like hundreds, thousands, millions of states are found, total validated, all is fine. Or it will give you result like there is an invalid state where this invariant is violated, and how to get into this state from the initial one following sequence of actions like send, send, receive, receive, send, and queue overflows. It will literally give you the failure trace, which you can later turn into your source code into a unit test, if you want. So, well, that's basically it. I did the same specifications for the task scheduler on the whole, and for multi-consumer queue. Most of the lines are comments explaining what is happening in this TLA plus stuff. You can find those specifications open source in this repository, which you can, there will be links in the end again. And also you can find there how to run TLA plus, how to write specs, well, looking at my examples, and where to study it. So there is a course of lectures from the author of TLA plus, who is still alive and supporting it, the runtime, Leslie Lampard. Some of you probably heard of it. And that lectures are actually fun. If you don't want to, even if you don't plan to use TLA plus, it's still worth watching. It's quite cool stuff. And now it's time for benchmarks. The cool stuff about those benchmarks is that they are comparative. I benchmark not just the new algorithms on some random benchmarks, seeing some numbers like millions per second, well, okay. I test those new algorithms against their trivial versions. Like, for example, the queues I benchmark against the trivial mutex locked queue. And the task scheduler I benchmark against a trivial thread pool with just a single queue, single mutex, no coroutines whatsoever supported, to see the difference, if my algorithms actually improved compared to trivial implementations. And I ran those benchmarks on 5 different hardware configurations with different operating systems, with tens of scenarios, all of which are available in the source code on GitHub as human-readable markdown reports, which you can also regenerate on your own system with just a single line Python script, which will generate those reports on your system if you want. Here we will just take a look at the few of the benchmarks, just some average results on an average machine used in my game. It's a Debian Linux with 8 cores running in Google Cloud. And we start from the front queue. So this benchmark of the front queue, it consisted of 5 producer threads and 1 consumer thread, doing busy loop pushes and pops to test worst possible contention. So despite the items are stored as stack, despite they are reversed on pop, it still was 1.5 times faster than a mutex locked queue. If I make it 10 producer threads, so I have more threads than CPU cores, it's the worst case contention for mutexes. It becomes 2.6 times faster, despite its shortcomings. What about the ready queue with 5 consumer threads, 1 producer thread, again doing busy loop pushes and pops? It is 2.6 times faster than a mutex locked queue. And also look at the mutex contention. It's multiple orders of magnitude lower, exactly because we take mutex lock once per multiple thousand operations, not on every pop, not on every push. And we can clearly see this result. So mutex is still here, but contention is so low that it's basically neglectable. And when I make it 10 consumer threads, it becomes 4.5 times faster. But, well, all this stuff takes us little how it will perform when it's joined together inside TaskScheduler, so we shall take a look at this one too. It runs on the same hardware. I mean, there are more benchmarks. I'm just showing you one of them, just a few on average hardware that we use. This benchmark had empty tasks, so just empty callbacks, again, to test worst possible contention in all points of the pipeline path. In the scheduler, when I had just 1 worker thread, which wouldn't be possible if scheduling wouldn't be migrating between the threads. So it works with 1 worker thread. It was 2.2 times faster than the trivial thread pool with just single queue, without coroutines. TaskScheduler, with all the overhead for the coroutines, was still 2.2 times faster. When I make it 5 worker threads serving those tasks, it becomes 3 times faster. When it becomes 10 worker threads, it is 7.5 times faster than a trivial thread pool with mutexes. And again, I remind you, this thread pool in the benchmark had no support for coroutines. And still, TaskScheduler performs it like that. If I would try to add coroutines into a normal thread pool with mutexes, it would be, of course, slower. But it wouldn't be fair, really. And as I say, those results are average. There are benchmarks when TaskScheduler is 10 times faster, when it's 15 times faster. There are other benchmarks when we have not so huge load of tasks, we have like hundreds, thousands per second. Then it performs almost the same as a normal thread pool. So it's not slower, it's not faster, there isn't just much load to compete on. But when the load becomes big, TaskScheduler scales and utilizes every CPU core to like 100%, while the thread pool would be a lot of time sleeping inside the mutex, inside the contending mutex. So, well, that is it. On the artificial benchmarks, there is also a real-life benchmark, real usage. Scheduler is currently used in every backend service in our game engine for handling requests and for internal long-running tasks, like when I mentioned I wanted it to be functional as just a single thread. It works for cases when I just have a few tasks which I want to wake up once per second and do something once per second. It's not huge load, I just want coroutines. So the biggest win was on one of the backend servers which I mentioned in the beginning, the save games case, when we got 10 times speed up in RPS from hundreds to thousands, and at the same time latency dropped 5 times. And that was just after replacing updater with TaskScheduler, even before further optimization. And another cool part is that this algorithm is extendable. So the stuff inside the blue circle, it's a thread safe space. As you saw, binary heap is not thread safe, but I still can use it because it is always accessed by one thread at a time. Here you can add next to the waiting queue epoll, or your completion ports on Windows, or libf from plain C. And then suddenly you get multi-threaded event loop. If you attach sockets to your tasks, you literally get multi-threaded event loop, which in fact we have in Ubisoft. It's just a fork of TaskScheduler plus epoll next to the waiting queue. It's very simple to extend for your use case. And about the future plans, they are not really huge. The algorithm already works just fine. It's just the implementations could be improved. We could use a port to ARM, although maybe it already works, I just haven't tried. You could also port it to other languages. Currently we only have C++, but it could work, I assume, in Java, C#, Rust. You just need, as I said, mutexes, containers, condition variables, and log-free operators. And could use optimizations like this front queue still bothers me that it stores items as stack and reverses them. Maybe there is a way to improve it. I just haven't found it yet. And that is the end. Thanks for your attention. And here you can find links to the source code, to the TLA Plus specifications, where to study TLA Plus, how to run it. Because original TLA Plus you can't run in command line, so you have to do some extra technical steps which are described there if you don't like the graphical interface. And also QR code to give feedback about my talk. And another link to this talk leads and to my other talks. And here I prepared some bonus sections, questions to myself, which I didn't fit into the main slides. But we can take a look at those if somebody will ask them as questions.
Thank you very much. Please, a round of applause for Vlad. We are extremely short of time, and I see lots of questions. So maybe one or two gentlemen over there in the red.
Yeah, hi. Just a short question about TaskScheduler, like algorithm. What about scheduling slippage, for example, when all workers are busy with some heavy tasks, nobody will schedule any tasks from the waiting queue, from a waiting schedule, right? So if we have some task with timeout, they will be timed out just because all the workers were busy, right?
Yeah, that will happen. When the task will be finally popped from the front queue by one of the workers, it will immediately see that it has expired, so it will go to the execution straight away without waiting queue. And you will see in your callbacks that it has expired. So tasks don't have to go through the waiting queue. They can bypass it if TaskScheduler sees that the deadline is already up.
Please.
I have a question about benchmarks. So you told us that Можно я по-русски спрашиваю? Мне сложно.
I can translate it, yeah, fine. Ask in Russian.
Вы проверяли, вот вы говорите, что ваша очередь работает быстрее, чем очередь, написанная при помощи мютексов. Вот. Вы использовали вашу примитивы, которые написаны в вашей open source библиотеке для этого или нет? То есть вот у вас есть, да, у вас есть open,
Yeah. He's asking if my benchmarks use mutexes and condition variables and other thread synchronization primitives from the standard library, or I have my own on which I benchmarked. So it's a complicated question. If I could use standard implementation, I would use it. But one of the conditions why I was allowed to open source it was to keep TaskScheduler exactly line by line how we have it inside Ubisoft. Even the order of inclusions, and the problem is that mutexes we have in Ubisoft and condition variables, they are not quite compatible with the standard mutexes, so they just have more features they're easier to use. So in this repository, they are implemented for Windows and for Linux using pthreads, critical sections on Windows, condition variables on Windows, and pthread condition variables on Linux. So they are, here is used what is behind the standard primitives, not them directly.
Тогда вторая часть вопроса. Дело в том, что я
Sorry,
посмотрел этот...
sorry. We're up on time. Unfortunately, I encourage you, everyone who has any more questions, grab our speaker, take his laptop, and ask all the questions that you have. Still, we had 2 questions, and you can choose a gift. Maybe. Can we give our speaker a gift so he can present it later in the discussion area for all the people here who want to ask questions? I think that would be better. Thank you, everyone. Thank you, Vlad. Don't forget to rate the talk. And see you later.